Thus far, we've talked about TCP error detection and recovery mechanisms and how that relates to high latency scenarios or dropped packets, lost communications, things of that nature. And those are all important. And we're going to kind of tie that together here when we talk about locating high latency sources. And it's important to note that when you're using network analysis, packet analysis, you're not always going to be able to find out what the problem is, but you may often be able to find the source of it. And that's okay. That's great, actually. Half the time spent troubleshooting and in many cases finding out what the source of the problem is, or at least where it's located so that you can dig into it and find out what's going on. So if you can locate it to a single host, you can figure out, okay, is there a process run amok? Is there something hung up that needs to be restarted? Is there malware installed on the machine? You can start figuring that out once you know which machine you need to look at. And trust me, that makes a big difference, especially when you're in a large network or maybe you're troubleshooting communication going across multiple hops, or when you really have to decide, is the problem on this workstation sitting right next to me, or is it in the server that's 1,000 miles away in the basement of a data center? So that really matters. So locating the source of latency, or at least trying to figure out where high latency may be coming from, is definitely important. And so we're going to talk about a little bit of a framework for that here. So I'm going to talk about a couple places you should consider when thinking about high latency and go through a framework using some TCP communication as an example that may be helpful to you. Once I'm done with that, you'll get a chance to practice that by doing a little bit of a lab exercise that I think is really fun. Latency, of course, refers to how long it takes for communication to get from one place to another. And we always have latency. So to say we're looking for sources of latency may be a little bit of a misnomer because you always have latency. No communication is instantaneous. But when I say latency, I'm particularly referring to high latency, which is what results in many of the things we've seen earlier in terms of slow communication, maybe potentially dropped packets, things of that nature. So when we want to talk about latency, there are a few different places that can come from in any given communication. The first is what we call wire latency, and that is what is occurring between two endpoints. So we have this notion of two endpoints. When they communicate together, that makes a conversation. Well, sometimes those endpoints communicate directly to each other, right? So they're on the same subnet, we'll say, and they're communicating directly. But oftentimes they're communicating across multiple networks, right? So everything in between that source and that destination, or that client and that server, is what we would consider wire latency, just because it's occurring somewhere in between the communication between those two endpoints. Of course, on the flip side, we do have client latency or transmitter or source latency, depending on what terminology you want to use. So that's latency caused by the client. So that means it's slow in sending a request or slow in processing data it's received, something of that nature. We also have server latency. The server is responsible for accepting requests and delivering data, perhaps, and maybe it's slow doing those things. So that's latency at the server side. When we talk about the measurable latency in any communication sequence, it combines all three of these things. So it's latency from the client, across the wire, and to the server. All those things combine to measure the latency that's actually occurring. And of course, you want that as low as possible. You want your communications as fast as they can possibly be. Now, that said, when you're troubleshooting, generally speaking, you're going to see a latency problem in one of these three areas when you encounter things running slow, right? It's not generally going to be all three. It's going to be, okay, the server was too busy and there's a lot of high server latency going on. The client was slow responding to a request and the application is bogged down and it was client latency, or it's something in between those that we don't quite know what it is, especially if we're going across the internet. Maybe we don't control all of the routers or hops along the way. So we have all these different latency sources that we need to consider. Now, a couple other things we need to consider. One, how many hops are between each endpoint? That's very important, especially as it pertains to wire latency. Theoretically, you'd think the more hops, the more latency, and maybe that's true in some cases, but really there's a lot more factors at play than that. A communication going through one hop can be much slower than communication going through 20 hops, depending upon how that data is routed and the health of the systems it's going through. But you do have to consider how many hops, where those hops are going. Hopping to Australia may be a little bit slower, or is generally notoriously slower than hopping to Europe, at least from the United States. Next, how much processing is required for each packet? We have the concept of TCP data packets and TCP control packets, for instance. Data packets have to be passed up to the application layer, and that data has to be stripped off and maybe passed off to an FTP server or a web server or a mail server. There's additional processing there. Control packets don't have any data. They're just processed by the network stack on the operating system. So a lot less processing there, and that is interesting to us when we examine latency sources. And you'll see that here in a minute when we go through the framework that we're going to go through. So you have to consider how much processing is required for each packet. Finally, what does normal communication look like? It's hard to determine if communication is abnormal if you don't know what normal looks like. So it's hard to say that there's high latency or the communication is slow if that's actually the norm. If for some reason you're going to a network that is just consistently slow, and that's a problem. Maybe your network's really fast and theirs is slow and you're having to traverse the network and that slows the communication down. Maybe you're dealing with an endpoint that is constantly overloaded, a really busy web server, for instance, or an application server that doesn't have enough bandwidth. If those things are, if it's normal for something to be slow, then that may be what you have to deal with unless you want to upgrade something. So understanding what normal communication looks like, understanding normal communication times, very important for being able to understand what is absolutely abnormal. Now, with that said, I want to flip over next to some actual packet captures and go through some examples of latency on the network or with network communication, and trying to look at the packets to determine what exactly is going on and what the source of that high latency may be. I've switched over to latency1.pcapng, and we're going to be examining a few different files to try to determine where high latency is occurring and where the source of the problem is most likely to be. But they're all going to be based actually on this capture, and although this capture is called latency1, it actually doesn't represent high latency at all. This is pretty expedient communication, and you can tell that by looking at the time column here. And notice we're looking at packets. If I go to view and time display format, we're looking at packets since seconds since the previous captured packet. So we're using that time display format, and that's what we'll continue to use throughout these exercises here. And notice the time deltas are pretty darn small. This entire communication sequence is happening fairly quickly. I mean, it can certainly be quicker, but there's nothing here that would lead me to believe that there's any slowness of communication occurring. Everything is happening in much less than a tenth of a second across these 6 packets. So we're actually going to take these same 6 packets and look at them in a variety of scenarios with differing time values. That's going to be the big thing we're interested in and how that has an effect. So the communication sequence itself is pretty straightforward. We have the establishment of a 3-way handshake, so a new TCP session between 172.16.16.128, which is our web client, 74.125.95.104, which is our web server. In this case, that's a Google IP, I believe. And then we have a GET request followed by some data being sent back and acknowledged from the server. So it's not the complete communication sequence. We don't actually need that. We just need these first few packets, and that's going to help us determine where the source of latency is. So I want you to pay attention to a couple things as I go through these next few examples. One is the source and destination. Where is the communication headed to when the latency occurs? The next is the time value. Where in the stream is latency happening? Where do we see the biggest time delta from one packet to another packet? And finally, the nature or makeup of the packets themselves. So is it a TCP control packet like these first 3 here, or is it one that contains application layer data like this HTTP packet, or one's sending HTTP data? So those are the 3 things I want you to be concerned about as we go through a couple of these exercises and as I switch over to the next packet capture. I've switched over now to latency2.pcapng, and this is a file where we definitely do have an example of high latency occurring in the communication. And we can see that here right off the bat in packet 2. We see that the delta between packet 2 and packet 1 is 0.87 seconds, and that is a lot, right? We don't want to see nearly a second elapsing in what should be some very quick TCP-based communication. Quickly perusing, we see we also have another example of that between packet 4 and 5. We see 1.15 seconds. So just to set up a TCP connection and make an initial GET request and receive a very little bit of data, we're taking over 2 seconds, and that's entirely too slow. Chances are that if a user is browsing to the internet and they're waiting on this process to complete, they're waiting a long time. The process is just going to be fairly slow for them to browse to this website that they're trying to browse to. So let's diagnose this and consider where the source of the latency may be. Now, we have 2 packets here where we see latency is occurring, and you might look at those and very quickly say, okay, 0.87 seconds, that's sent from the server, 1.15 seconds, that's sent from the server, the server is the problem, but that's not correct here. And that's a common mistake people make is they say, okay, here's the time delta. So the source is the server, so it has to be the server, but that's not the case. You're not concerned about this particular packet, actually. You're concerned about the delta between the two previous packets. Remember, that's what we're concerned about. So we're concerned about what's happening between packet 4 and 5 and what's happening between packets 1 and 2. So let's think about that a little bit. In this case, when packet 1 is received by the server doesn't have to do a lot with it. And the reason is because this is a TCP control packet, right? It's just a TCP SYNAC, which has no data. It's being processed by the network stack on the system, the TCP IP stack. It's not being handed up to the application layer protocol. So there's actually no opportunity here for the web server software, whether it's Apache or what have you, there's no opportunity for it to get the data and introduce latency into the equation. In this case, the latency has to be occurring in some other way, right? Because it's not an application layer type issue. So that's what we have here in this case. Now we have a similar case happening here in packet 5. Notice that between packet 4 and 5, we have a GET request and then we have an acknowledgement. And you may say, okay, well, this is HTTP, so clearly the HTTP server is dealing with that. And again, that's not the case here because remember, TCP acknowledges the data it receives. So this is being acknowledged again with the TCP IP stack on the server. So that's what's responding. It's not the web server. The web server starts responding down here in this 6 packet where it's actually sending data to the client. And that's actually happening pretty quickly. Look at that, 0.01 seconds. So that's happening very fast. The delay appears to be, in this case, with the networking stack on the remote system. And that's not really a feasible thing in most cases, right? So that's actually not going to be the issue here. In this case, this is an example of wire latency. So this is latency occurring between the client and the server, somewhere in between. We don't know where. We're going from a local device out to the internet, so there's probably quite a few hops going on there. But in this case, this is wire latency because we see that the slowdown is occurring when no application layer data is being processed. And that's important. And this isn't a 100% thing, but generally in almost every instance I've seen, when you're capturing packets and there's wire latency, you'll see evidence of it, generally as early as the three-way handshake here. And you'll see it often when you're looking at the packets that are the response from the server, wherein you're just getting normal acknowledgments and TCP control type packets back. So hopefully that makes sense and isn't too confusing. But the key note here is we're concerned about what's happening when we see the latency between that and the previous packet. In this case, it's very simple processing by the server. There's no real opportunity for the server to introduce latency. So you know it has to be, by process of elimination, wire latency in this case. Now we're looking at latency 3.pcapng, and this is a different scenario where we have high latency, but it's coming from a different source. A quick look at the time column, and we see that packet 4 is where the large amount of latency is reported, in this case 1.34 seconds, which is far too much. Once again, we're concerned about what's happening between packet 3 and 4. In this case, the source is the client, 172.16.16.128, and it's sending data to the server. So what's happening here? Well, we have our client who set up our initial three-way connection, and that was completed pretty quickly, right? The very low time deltas here for our first 3 packets for our SYN, SYNAC, and ACK. And then we have our client who is responsible for making the next move, right? It initiated the connection to this web server. It has to make some type of request, whether it can be a GET, a POST, what have you. In this case, it looks like it's a GET for the web root directory here for /. And that's where the big delay is occurring. The web browser, or something related to it in this case, something dealing with the HTTP protocol, was significantly delayed. So that's the issue here, which tells us that this is an issue with client latency. The client was responsible for the processing that occurred between packets 3 and 4, and that took 1.34 seconds before it could get this initial GET request out. Otherwise, everything looks fine. The three-way handshake looks fine. The data being sent back from the server looks pretty fine. So we know that there is an issue here with the client. We have an example of client latency. This one's maybe a little bit more straightforward than the last one where we looked at wire latency. So hopefully that makes sense to you. So let's look at one more example of latency, and I think you might be able to guess where it's coming from. Okay, so now we're looking at latency for .pcapng, and this is the last packet capture we'll look at in this example, and then I'll kind of recap everything and describe the overall framework of what we did. Now, this one, we look at the time column and see that the last packet is the culprit. So we're concerned about what's happening between packets 5 and 6. So let's walk through this communication and what's going on. We see that the client initiates the connection to the server, and we have our three-way handshake, which occurs very quickly, very expedient, no problems there. The client initiates a GET request to the server, and again, also very quick. We see an acknowledgement from the server. Again, this is a TCP control packet, so it's not being processed by the application layer protocol. It's only being processed by the server's TCP IP stack, and that is also very quick. However, it's what's occurring between packet 5 and 6 that is interesting. And the difference between 5 and 6 is that 6 is not just a TCP control packet. It actually contains data. And when I click on that here, you can see down here we have 1406 bytes of TCP segment data. And if you see where my mouse is, it looks like this is clearly HTTP response data. We see HTTP 1.1, 200 OK, and we see some HTTP line data fields. So pretty neat. So that's our HTTP data. So we know that what's occurring between packets 5 and 6 is actually involving higher layer processing on the server. So it's actually the web server application, whether it's in Apache, Nginx, IIS, whatever, it's having to process the data. That tells me that the delta between 5 and 6 is caused by the server. It's server processing, which is the delay in this case, and it's that server which is introducing high latency and slowly sending data back to the client. So we know in this case, the server is the problem, and that's different from our previous examples wherein we saw wire latency and client latency. In this case, this is server latency being introduced into the equation. Hopefully those examples made sense and you're able to follow that. But if not, I have what I think is a little bit of a simpler way of describing them here with the diagram you see on the screen. This is what I call the latency locating framework. Very straightforward. I didn't necessarily come up with these concepts, but I do put them into this diagram because I think it makes much clearer sense on where the issue might arise when you're trying to locate latency. And this really encapsulates everything we just went through. In this case, and really in any case with the TCP-based communication, if you want to determine the source of latency, you can really do it with just a few packets. In this case, just 6 of them, just like we did. So we have our initial three-way handshake to set up the connection. We have our layer 7 protocol request, the acknowledgement that comes back from that, and then the layer 7 protocol data that results. Now, this is based upon a request response type layer 7 protocol. You can adjust it if it's the other way around, maybe if it's a push instead of a pull or something like that. But this is kind of normalized for any layer 7 application protocol. You see here that if we want to locate wire latency, we're generally going to see that manifest in the SYNAC that comes back during the initial three-way handshake or in acknowledgement packets that come back from the server. That's where we would see wire latency because that's where we know minimal processing is happening by the server or the client. It has to be something in between that's causing the issue there. If you see where number 2 is there, the layer 7 protocol request, that's where we will find client latency, any request from the client to the server. So we look at the previous ACK, and then we look at the delta between that and the layer 7 protocol request. And if there is a large amount of time there, we know we have a client latency. Finally, we have server latency identified by the number 3, and we'll see that anytime we see a large gap between acknowledgements and data being sent from the server to the client. That's when we know processing is occurring at the application layer protocol level with the server, and that's where we're going to find server latency. So this is an example of this framework. You can extrapolate this out. It doesn't have to be at the beginning of the capture, but that's certainly a great place to do it. Now, one thing to note, just because a connection starts fast doesn't mean it'll always be fast. So sometimes you won't be able to look at the beginning of the capture. You have to look at the middle and look for signs of these things as well. But if you'll keep in mind the factors we talked about, looking at the time column, looking at the deltas there, looking at the direction of the traffic, the source and destination, and considering the processing that's occurring of the data between the 2 packets you're looking at, that's really going to be your best bet for finding latency on the network when dealing with TCP communication. Now you might ask yourself, okay, well that's TCP, but what about things that are not TCP? Well, that gets a little trickier. We discussed that a little bit at the beginning of the section. UDP, of course, unreliable darn protocol, and since it's unreliable, we don't have as many options for locating latency there as we do with TCP, which makes that a little bit more of a challenge. But nonetheless, if you are concerned with reliability, hopefully you're using a protocol that is reliable by nature and it's using TCP, and you can use this framework to diagnose those types of issues. That's going to do it for this section on locating high latency sources. I want to encourage you to go through the labs on this one. I think this is one of those things that when I talk about it, that's great, but until you actually get hands-on and actually look at some of these packets and try to guess where the source of the high latency is based upon these deltas between the packets as relates to time, I think once you do that hands-on, it really drills this in. So I don't always say this, but definitely make sure you do the labs on this one. Go through the exercises, dig through those, answer the quiz to see if you're right, and I think that will help you grasp these concepts quite a bit better.